Hey, my name is Alexander Castro, and I'm going to explain entropy in my own words. So the question is, what is entropy? In order to understand entropy, we have to understand the first and second law of thermodynamics. So the first law of thermodynamics states that the energy of the universe is neither created nor destroyed, but it can be transferred from one form to another. And the second law of thermodynamics states mathematically that delta S, which is entropy, is equal to K natural log of W. And this helps predict whether the reaction is spontaneous or non-spontaneous. And what I mean by spontaneous is that no energy is required in order for the reaction to occur. And non-spontaneous is where energy is needed from an output source in order for the reaction to occur, which is not likely. So that gives the definition of entropy. So entropy is a state function that increases randomness of the phase space over time. What phase space means is the different random configurations that energy can be dispersed and rearranged. So for instance, in this little diagram, we have one phase space and another phase space. So entropy will leave or exit phase space 1 here and enter into phase space 2. So you see that the energy is dispersed and randomly arranged in however it occurs. So with that in mind, we can see that entropy is always greater than 0 or positive. So in an exothermic reaction, we see that the system is releasing entropy going into the surrounding, and therefore the surrounding is increasing the entropy of the universe since it's always positive. In an endothermic reaction, the entropy is going from the surrounding to the system, but overall the entropy of the universe is positive since the surrounding energy or the negative of this is always greater than the positive of the system. So in other words, entropy in an exothermic system always increases its surrounding system, therefore increasing the entropy of the universe. So with this, we can use the equation of Boltzmann equation, which is what I said previously. Delta S is equal to K natural log of W, where K is a Boltzmann constant. The Boltzmann constant is basically the ideal gas law, the R constant of the ideal gas law, which is 8.314 joules per mole, or Avogadro's number, which is 6.022 times 10 to the 23 moles. So here we know that moles cancel out, and you're left with 1.3 times 10 to the negative 23 joules per Kelvin, which is the unit of entropies. And W is just the randomness of the system of the phase space, which in other words is the probability of how the energy within that phase space will arrange. And that is unitless. So here delta S entropy is joules per Kelvin. So since the entropy in the universe is always positive, then we can say that the entropy of the universe is equal to delta, or entropy of the system, plus entropy of the surrounding. And this relationship gives us, or states, that entropy is inversely proportional to negative delta H of the system, which is enthalpy or energy, and that entropy is also inversely proportional to 1 over temperature in kelvins. So that is important to understand, because then it gives us an equation that leads to that the entropy of the surrounding is equal to the negative delta H enthalpy over temperature at a constant pressure and temperature in kelvins. And this links the relationship between enthalpy, delta H, and entropy of the system. Since we know that entropy of the universe is equal to entropy of the system and the surrounding, and we know that the surrounding is equal to negative delta H over temperature, we can plug this equation into the universe equation of entropy and get a new equation of negative T delta S of the universe minus negative T delta S of the system plus delta H. So basically what we did is just multiply the equation, plugged in the enthalpy equation to the surrounding multiplied by a negative T to get rid of the temperature and turn it into positive and made the system into the negative temperature. So this equation here gives or states or gives free energy, and gives free energy. Yeah, so it's Gibbs free energy is equal to negative T delta S of the universe. So simply putting delta G, Gibbs free energy is equal to entropy minus delta S, negative T delta S, where delta H is the entropy. Therefore, Gibbs free energy is directly proportional to the negative temperature in kelvins of the entropy of the universe at constant pressure and temperature. And with this, we can use or simply state that Gibbs free energy can be used to predict whether a reaction is spontaneous or non-spontaneous. And this will lead to an increase of entropy of the universe, which links it back to the second law of thermodynamics. So how does this relate to equilibrium reaction? Well, Gibbs free energy from an equilibrium reaction, first we need to understand what an equilibrium reaction is. So here there's a basic equation. We have the reactants going at equilibrium to form products and vice versa. So you have your K constant forward and your K constant in reverse. So the rate law states that the K constant forward times the molar concentration to its moles is equal to, of the products, is equal to the rate constant in reverse, K constant R in reverse, times the reactants products to their molar concentrations. But this is only true at equilibrium. So since it's true at equilibrium, we can have a ratio of K forward and K reverse. And this basically gives a similar equation of the law of mass action, which is also equal to the K constant or the equilibrium constant. So in other words, the equilibrium constant is a molar concentration of the products over the molar concentration of the reactants. When considering a gas reaction, then we use the equilibrium constant of pressure, and it's basically the same thing as molar concentrations, but here we just take the partial pressures of the products and partial pressures of the reactants, which gives the equilibrium constant of the pressure. So by knowing this, we can link that to free Gibbs energy in this diagram. So this diagram states that the overall Gibbs free energy standard is on the y, and then time on the x. And over time, the reaction will reach an equilibrium. So since delta G at equilibrium is equal to 0, then that means that negative delta G standard is equal to negative delta G plus delta G. So then you have your negative delta G standard is equal to negative delta G plus 0, since delta G is equal to 0. So then with that said, that means that the negative delta G standard or overall is equal to negative delta G at the equilibrium constant K, which is here. So then, and since the overall standard of negative delta G is negative, that satisfies the second law of thermodynamics. So then we can see here from this graph that if K is greater than 1, that means that the equilibrium or the reaction favors the products or shifted right and will be shifting left. If K is less than 1, that means that it favors the reactants, so the reaction is on the left side, meaning that it shifted left and will be shifting right. And when it reaches equilibrium, then it reaches K, so delta G is 0 at K. So since at equilibrium, we know that delta G is 0, we can plug that into this equation, which is free Gibbs energy is equal to delta G standard of the reactions plus R natural log of Q. And this is under non-standard condition and when the reaction is occurring. But since we know that the reaction is at equilibrium, we can plug in delta G to 0 and have the reaction or Gibbs free energy standard reaction plus R natural log of K, and we replace Q with K since at equilibrium here we know that Q approaches K, which is similar, so they're equal. So the overall equation at equilibrium is delta G standard reaction is equal to negative R, which is the ideal gas law constant, times the natural log of K at equilibrium. So with this is one way to find out how to calculate Gibbs free energy. But other ways to calculate the standard Gibbs free energy is by using their formations or the delta G standard formation. So if you have your equation, then you have you add the sum of the products of delta G standard of formation of the products times their moles or their molar coefficients from the equation minus the sum of the molar coefficients of delta G standard formations of the reactants. And that would also give you the delta G standard reactions. Another way, like I said previously, under non-standard condition is just delta G reaction is equal to delta G standard reaction plus R, the ideal gas law, temperature in Kelvin, natural log of Q, which is not in equilibrium. And then the final at equilibrium is delta G standard reaction is equal to negative R times the natural log of K. And the only difference between delta G standard and delta G is that at standard conditions, delta G is at 1 mole per atom per 25 degrees Celsius. So these are many different ways to figure out whether a reaction is spontaneous. And since we know delta G is similar to entropy here, then we can use that as a way to figure out what entropy is. Thank you.